Hi everyone and welcome to Cognify. In today's session, we're going to be looking at a few questions, right? We'll be covering Euclidean geometry, a bit of trigonometry and Euclidean geometry, right? So some students struggle with this area, especially when it comes to geometry. So I'm going to try and take a simplified approach and explain concepts to you, right? So these concepts should help you to tackle other type of questions that might require you to utilize a bit of geometry, right? So in the first question, we are given a circle with center O. Okay, so we've got a circle with center O and a chord of length 8 centimeters is 3 centimeters from the center. What is the radius of the circle? So if we check here, right, we've got a chord. So what is a chord? Okay, so that's an important concept for you to understand. A chord is basically any line, okay, within a circle that goes from a point on one circumference to a point on another point on the circumference of the circle. So if we check here, right, our chord is, if we can label it, we'll say, let's say this point here is A and this point here is B. So AB would be our chord. Another chord could be this here, right? So it's basically drawing a line from one point, the circumference, to another point. Yeah. So that is our chord, right? And it is 8 centimeters long. Okay, so let's write that down here. AB is equal to 8 centimeters. And next, it says that this chord is 3 centimeters from the center. Okay, 3 centimeters from the center. So if we check here, right, since I've already drawn it, you can clearly see here that this chord here, it's a particular distance away from the center, right? So that we can define it as the center, we can say it's O. And this point here, where the radius and the chord intersect, we can call that point, let's call it C. Okay. So now OC is equal to 3 centimeters. And note that this is not our radius, right? But it is part of our radius. So now we want to find the radius of the circle. Okay. So in order to find the radius of the circle, let's put a point here as well. So AOC lies on this radius. Okay. So our radius goes from O all the way to D. Okay. So OD is our radius. Okay. Radius. Okay then. So now we want to find our radius. So we need to do a bit of calculation here. Okay. So let us see. If we check here, right, we want to find our radius. Okay. And our radius is, if we were to consider all the points here, OCD, our radius is OC plus CD. Okay. So if we were to find, if we were able to find CD, we'll be able to find our radius, right? Because OC, we already know what that is. It's 3 centimeters. Okay. So now let's see here, right? Let's try and see, because even this line here from O to B is also radius. Okay. So note that this OP, okay, is also equal to the radius. It's good to break this up and understand the concepts like this, okay? So R is also equal to OP, okay? So we can use it, either use OP or OD. So now let us quickly check here, right? You remember that OC is equal to 3, right? And AB, which is our chord, is equal to 8, right? But what if we can get this point here, the length from C to B? Okay, from C to B, what is it? Okay, so now another concept that you might be familiar with is radius bisecting a chord. Okay, so what you need to note is that anytime a radius and a chord intersect, okay, that intersection, okay, basically breaks up the chord into equal increments. What that means is that CB and AC are equal, okay? Because when the radius bisects the chord, it bisects it at 90 degrees. So from this, we can clearly see here that CB is equal to what? Half of 8 centimeter is 4. Okay, so 4 is there and 4 here. Okay, so now we've got OC and CB. So now we can simply just use the Pythagoras theorem, you see. So let us go ahead and find it, right? So OB is equal to OC squared plus, you go square here, CB squared. So now let's continue this here. So now OB is equal to the square root, okay? So now OC squared is what? OC is 3, right? So we're going to have 3 squared plus. Next is CB. CB is 4. So that we square it. So what do we have here? We have 9 plus 16. And the square root of 25 is equal to 5. So that is our solution. So you see when you break this up, right, by drawing a diagram, putting down all these points and the values, you can have a high level view of all your different parameters, right? All the information that you've added, and you can then see how everything links up. So let us continue to the next one. In the next question, we have a triangle. A triangle, okay, so defined as ABC. Okay, side B is equal to 7. Okay, so now let me just quickly explain this to you. So these sides, right, it's going to be opposite to the angle. So here we've got angle B, right? So opposite to it, it's going to be the length of B. So here B is 7. Okay, next is C. You see C here, opposite to that is this side here. So C here is equal to 10. So the lowercase c denotes a scalar quantity, right? Length, and then c denotes the angle. So now what we want to find is the area of the triangle. Another thing we are given is the angle here, okay? Which is 30 degrees. So we are given 2 sides and an angle. So now we want to find the area. So the area, okay, there's this formula that I'm sure a lot of you are familiar with. If you are given 2 sides, right? We've got AC and B, AC and AP, okay? So we've got 2 sides here, okay? AC and AP, okay? What we do, we use the standard formula, all right? And we multiply by sine of A, okay? The reason is, right, we look at where everything is positioned. We've got the angle here, right? It is 30 degrees and we've got these 2 sides. Since we have all of these here, we can then find the area, okay? Same thing if we were given the angle B, okay? Let's say B here is, let's say 40 degrees, right? And the side here is 6, then we've got this side here 10. You can still find the full area, the same area using the other info you have, right? So in this case here, we've got angle B, right? So we're gonna say BC times BA times sine of B, because these 2 sides here are adjacent to this angle. Okay. But anyways, let us find the area here. So the area here will be what? I'm just going to rewrite this as half BC times sine A. So this will be a half. B is 7, C is 10, and sine of 30 degrees. So now this will be half times 7 times 10 is, I'll just write it as 70 over 2 times a half, because sine of 30 degrees is a half. Okay, so now this is 70 divided by 4, which is 17.5. And always remember to include your units. Okay, in this case, it should be example 1 given the unit, so we'll just leave it as unit squared. So that is basically our answer. So you just need to remember what formula to use, right? And what parameters to include, okay? Because in this formula here, we are considering the two sides that are basically next to this angle. If you were to use C, okay, you angle C, you then use B and BC, this point here, 6 and 7. But that's basically it, okay? So let us have a look at the next question. And find the solutions for it. So in this question here, what are we given? So we are given O as the center of a circle, and we've got points A, B, and C that lie on the circumference. So we've got this point here, we'll call it A. We've got another point here, we call it B, and we've got another point here, we'll call it C. So all these points lie on the circumference, and we've got only as the center. Okay. So now if the angle at the circumference ACB is 40 degrees, what is the size of the angle at the center? So it's good to visualize this, right? So let us join our points here. Okay, so I want to make this neater. So let us align. We've got that line. So we'll reduce this thickness, change the color. Okay, and we've got one there. Let's see if we can put another one from here to there. And lastly, from here to there. So we've got a triangle. So what does it say here? It says if the angle at the circumference ACB. So we've got ACB. So this angle here, if it is 40 degrees, so we'll put a 40 there. If that angle is 40 degrees, what is the size of the angle at the center AOB? Okay, so we're going to have AOB. So let us include another line here, right? So we'll have, and just put a different color for this one. Let's make it purple. And another one. There we go. Okay. So now we can see here clearly. So what is the size of the angle at the center AOB? So AOB. So we want to find this here. What is that angle? Okay. So let me just remove this part since we know where the center is. So the way to do this, right, is to apply the theorems that you've learned, right, in Euclidean geometry. So we want to find the size of the angle at the center, okay, given the angle we have at the circumference. We are given nothing else, okay? So this is where we implement one of our theorems. So the theorem that we're going to consider here is the angle at the center being twice the angle at the circumference. And visually, when you look at it, you can clearly see here that the angle at this point here looks almost twice as big. Okay. So now the way we're going to write this here, right, is that angle AOB, okay, is equal to twice the angle at ACB. ACB. And then we need to give a brief reasoning for that, right? You can say angle at center equals twice angle at the circumference. So what is the answer here? It's simply going to be 2 times 40, which is equal to 80 degrees. So that is our answer. And that is basically it. Okay, so in this example, it was quite simple. We simply applied one of the theorems, okay, Euclidean theorems. So that's why it's important to understand all these different theorems that apply to geometry, particularly circle geometry. Okay, so you're going to be utilizing it in different cases, right? Another theorem is the one we covered previously was the radius, okay, bisecting the chord. And when you experiment with that, right, you will clearly see that it does actually bisect the chord. Okay. Another one is tangent to a circle. The radius, when it touches a line that is tangent, let me just quickly show that here. Let's say we've got a line, right, that is coming from there and it touches the circle there, right, at that point. So now if we were to draw a line from the center to that tangent line, that angle is 90 degrees. And you can test this out, okay? And another thing is, let's see all the angles. You know, if you've got, let's say you have, okay, a quadrilateral, right? So you've got all these points here that are, let's make this match. So if you have 4 points, right, on a circumference, when you join all of them, you get this, right? It looks like a square because it has 4 sides. So for all these points, right, if you take an angle, if you take all the internal angles, the angle that you have here, the angle that you have here, here, all these angles, when you add them up, they should add up to 360. But you're quite familiar with that, okay? Because the internal angles of a quadrilateral, they sum up to 360. But you see how all these concepts, you can utilize them even in circle geometry, okay? We can even expand this line here, okay? The angle here would be equal to the angle opposite this angle here, which is there. But anyways, we will tackle such theorems in detail in a different video, but I just wanted to give you some highlights on it. But that's basically it for this session. Thanks for joining me and till next time.